Saludos y muy buenas tardes a todos los seguidores del EcoExploratorio Museo de Ciencias de Puerto Rico. Gracias por estar conectados al programa de ciencia virtual a través del cual disfrutarás de la educación en línea participando de nuestros diversos webinars y talleres interactivos. Semanalmente tendrás la oportunidad de aprender sobre diversas temáticas STEM como salud, las matemáticas, el espacio, los fenómenos naturales y el COVID-19, entre otros temas. Esta semana, el tema de la semana es edición calor y pues los horarios para los webinars son a las 11 de la mañana, a la 1 de la tarde y ahora el de las 3 de la tarde. Recuerden seguirnos a través de las redes sociales de Facebook, Twitter e Instagram para que te enteres de los futuros eventos que tenemos para ustedes bajo el programa de ciencia virtual. Si deseas volver a ver esto o alguno de los pasados webinars, visita a la galería de videos en el Facebook del EcoExploratorio y síguenos en YouTube para que recibas una notificación cada vez que publiquemos un nuevo video. Accede a nuestra página web que es el www.ecoexploratorio.org/ciencia virtual. Para más información, pues mi nombre es Michelle de Jesús Ortiz, junto a nuestra querida Ada Monzón, pues vamos a estar aquí moderando en el día de hoy. Y quiero que sepan que esta semana podrán participar libre de costo de otros webinars que también tenemos, que va a haber uno que se llama La flora y fauna ante la sequía, con nuestro explorador Roberto Sánchez. Ese va a ser a las 11 de la mañana. También tenemos a la 1 de la tarde el calor en las zonas urbanas y cómo disminuirlo, con nuestra ecoexploradora Esmeralda Torres. Y a las 3 de la tarde el recurso Ernesto Díaz, director de Oficinas de Manejo de Zonas Costaneras y Cambio Climático del Departamento de Recursos Naturales y Ambientales. Él va a estar hablando sobre la ruta hacia la resiliencia ante el cambio climático. Para que sepan, compañeros y compañeras, pues este web va a ser totalmente en inglés. Y pues al webinar de hoy, pues puedes enviarnos tus preguntas en la sección de Q&A, Questions and Answers, si estás participando a través de Zoom. Y si nos estás viendo a través de Facebook Live, puedes hacer lo mismo vía el área de comentarios. Escogeremos algunas de sus preguntas para ser contestadas en vivo al final de la presentación. Ahora les dejo con Ada para que ella presente aquí a nuestros recursos. El micrófono, Ada.
Yep, now I'm good. Muy buenas tardes a todos, es un placer estar con ustedes. Muchísimas gracias, Michelle, por estar de moderadora. Michelle es nuestra coordinadora STEM en el EcoExploratorio, Museo de Ciencias de Puerto Rico, y en este programa, Ciencia Virtual, hoy estamos iniciando una nueva edición, como mencionó Michelle, que es sobre el tema del calor. Y usted se preguntará, ¿pero por qué hablar del calor? Si el calor lo sentimos todo el tiempo. Miren, el calor se ha convertido en un problema de salud pública y es posiblemente relacionado a la salud como uno de los temas más importantes en el mundo entero, porque nuestras temperaturas globales están aumentando. Y por tal razón, tenemos que estar seguros de que tomamos acción, entendemos y tomamos acción, porque esa es nuestra nueva forma de vida. Fíjense ustedes que hoy estamos hablando de nuestros recursos de agua, cómo la evaporación de los embalses inciden ahora en un posible racionamiento si no vemos la lluvia, y esto pues va a traer consigo una serie de inconvenientes a todo lo que es el manejo de nuestra sociedad y nuestra calidad de vida. Y por eso pues estamos encantados de que el recinto de ciencias médicas del doctor Pablo Méndez haya hecho disponible a todos estos recursos que están bajo una gran propuesta de educación e investigación del tema del calor y su impacto en la salud. And we are delighted this afternoon to have Dr. Zack, Guido, Assistant Research Faculty from the Arizona Institute of Resilience. Él es el doctor Zack Guido es uno de los catedráticos de la Universidad de Arizona y específicamente del Instituto de Resiliencia de Arizona. He has active research in the Caribbean, Africa, and Southwest United States. Él tiene investigación activa no solamente en el suroeste de Estados Unidos, pero también en África y en el Caribe. O sea, es un científico internacional y nos enorgullece el tenerlo aquí en la plataforma de ciencia virtual. He will be talking to us about the climate system, how it works, the role of heat, and the main features of the Caribbean climate. O sea, él nos va a estar hablando del sistema del clima, que recuerden que es bien diferente al tiempo. El tiempo es soleado, nevando, lluvioso. El clima son los promedios de los elementos de temperatura y precipitación por muchos años en un lugar, cómo trabaja, cuál es el rol del calor y sobre todo cuáles son esos elementos principales del clima del Caribe. We welcome you, Zack, for being here with us and educating our audience about the topic of climate change and also heat. Thank you.
Thank you very much, Ada and Michelle. Should I share my screen now?
Of course you can.
Okay. And thanks everybody who is joining us during your afternoon, my midday. Very much appreciate your time. And lastimadamente, I'm going to speak in English because my Spanish needs a lot of practice, and I couldn't give this in Spanish. So bear with me. I will try to talk slow. I purposely did not drink as much coffee as I usually do. So yeah. So as Ada mentioned, my talk today is going to be sort of the big picture and thinking about the climate system and specifically how it works and the role of heat in that. And when we talk about those two things, we'll also talk about how they influence some of the main features that you all experience on a yearly basis in Puerto Rico. So I'm coming to you. Let's see here. I'll show this. I'm coming to you from Tucson, Arizona, and we are now entering our heat season. And I just plotted up here some data from the first 10 days of May, and it's been one of the hottest 10 days on record so far. And these bar charts just show you the range of daily highs and daily lows, and they normally fall within that brown range there. And so we've experienced every single day for this month above average, sometimes 10 to 12 degrees Fahrenheit above average. So this is the time of year in which nobody envies living in the desert of the Southwest. So that's a picture of my my city there on the right. So hopefully it's a little bit nicer where you are. The only thing that we've got going for us is it's a dry heat. We don't have the humidity that you all have. So temperatures when they're elevated at 106, which they were a few days ago, it could be worse. It could be 106 with a lot of humidity, and then it feels a lot worse than that. So before getting into the presentation, I just wanted to provide a little bit of context of how I got interested and how I had the opportunity to start working a little bit with Ada and some other colleagues in Puerto Rico. And I've had the opportunity to lead a project starting about 2 years ago that was trying to think about how weather and climate information can help inform public health decision making and the concerns of public health. And it's a collaborative project with the University of Puerto Rico. It's funded by the National Oceanic and Atmospheric Administration. And we've got a whole bunch of collaborators, including at my institute, University of Arizona, among others. And what we did is we've hosted a few workshops there. The most recent one is a photo from the one that we hosted before the world changed in February 19th at the EcoExploratorio. And we brought together some people to talk about some of the risks related to heat and public health. And one of the things that we talked about quite extensively was just that there might be more of a concern about heat than many people recognize in Puerto Rico. And that's kind of obvious because most people that live in Puerto Rico have experienced the climate there, and it's hot year round, obviously more in the summer, but there's a certain level of acclimation that happens. But nonetheless, there is quite a bit of public health impacts that are associated with just a few degrees change of temperature. And we started to explore that. And really, again, the idea was, is there knowledge about the climate and about the weather that we can bring to bear on creating awareness of heat, doing a little bit of education. And so that has prompted some of our team members to do some research related to heat. And you'll hear from some of those talks if you're able to attend these webinars throughout the week. Just call out a few of them. Our colleague from the University of Puerto Rico, Pablo Mendez Lazaro, will be talking about heat and public health impacts on Friday. And a colleague from the Caribbean Institute of Meteorology and Hydrology, Teddy Allen, will also be talking about the relationships between hurricanes and heat. But there's a whole bunch of other talks. You've probably seen the agenda. There's a lot of fascinating talks in the next week. So hopefully you can attend more than one. So with that, hopefully I can give a little bit of a foundation talking about it from a general perspective about the climate system. And some of these slides are from lectures that I give my 200 level undergraduate class here at the University of Arizona. So I'm packing a lot of information into a few slides. But hopefully it piques your interest and you learn something, and you can go out and watch some YouTube videos, or we can answer some questions in the Q&A. So the two things that I really want to focus on today are what drives the climate, and I'm going to emphasize the role of heat, because it does play a big part in driving the climate system. And then we'll transition in talking about how the sort of general circulation of the climate relates to the main characteristics that influence climate in the Caribbean. All right, so I got a short video that I want to show for you, 15-20 seconds, and it's just an animation of the winds circulating the globe. That should show up on your screen momentarily. There we go. And so what you're looking at, we're looking down on the North Pole as it's rotating. You can see the winds, really fast winds, are in redder colors. And you can see that there is this sort of wave-like structure, really cool wave pattern that sets up. These are our westerlies, but you can also see quite a bit of these whirlpool-like circulations that happen right off Baja, California, right here, if you can see my cursor. And there's a number of other ones that set up. So this is the general circulation of the atmosphere, and the winds circulate that globe at various strengths, and they move around. And so the question is, why? What controls this? So that's what we're gonna talk about. Okay, so there's quite a bit of nuance to it, but if we think about the foundations for what's driving the winds, it's really a couple key features. The first one is that we live on a rotating globe. So the Earth rotates, and that helps influence the direction of the winds. We also live on a planet that has both land and water, and those masses end up responding differently to the sun's energy. And because we don't live on a perfect circle, we live on a sphere, all of those things combined ends up creating this uneven distribution of heat across the globe. And so as a result, the climate system basically sets up to move that heat around. So that is the principal function of the climate system. It's to move heat from where it accumulates more to where it accumulates less. So we're going to explore that. Basically, obviously, many people know this, but the vast majority, nearly 99.9% of our energy comes from the sun. There's slight variation, maybe 0.5% over very long geologic timescales of hundreds of thousands of years. But principally, the sun is what drives our energy. And that sun, that energy is of a particular form. It's of an electromagnetic form, and it streams through the vacuum of space, and it strikes our Earth. And that sun is absorbed by the Earth, and it warms. The Earth warms. So all materials, unless they're perfectly white, perfectly reflective, they absorb that electromagnetic energy and they convert it into heat and they warm. Some warm more than others, some warm less. The land warms at a faster rate than the oceans, for example. And those materials then give off heat, and that heat is of a different form. It's not this high energy electromagnetic form. It's a longer wavelength, and that'll be very important as we talk later in the presentation. So the energy from the sun strikes the Earth, it warms, and it absorbs that energy, it warms, and then it gives it back off. Now, being a sphere, the energy of the sun is not, it doesn't strike the Earth the same everywhere. So you can think of this like at the equator, the Earth's or the sun's energy has a more direct strike with the Earth. And so if you have the same amount of energy at the equator as you do at more northern regions, there's a higher concentration of that energy at the equator. And so you can just visually see this where the area, if you're seeing my pointer, the area at the equatorial region is smaller than the area of that light over the northern regions. And so the same amount of energy is coming in, but over the northern regions, it's getting spread out over a greater area. So there's more direct at lower latitudes and more oblique at higher latitudes. Okay, so you can also think of this like a flashlight. If you point the flashlight perpendicular to a surface, it's going to concentrate all of that light. It's going to illuminate that surface very brightly where that light is shining. Versus if you change the angle of your flashlight, it's going to illuminate a larger area, but more dimly. So it's the same principle. And so basically, it's the sun's angle and how high the sun is in the sky determines the angle that the sun strikes the Earth, and how much energy, therefore, is either concentrated or spread out. And so this happens both during the day. At midday, we have more direct sun than in the early morning or early evening. In the summer, we have more direct sun than we do at the winter. And if you're at the equator, we have more direct sun than at polar regions. So that concentration of energy is, like I said before, is different depending on the time of year and where you are, time of day and where you are on the globe. Okay, and so this matters for a couple reasons. So this is a figure on the x-axis here is our latitude. So 0 is the equator, and as you move left, you go toward the North Pole, and as you move right, you go toward the South Pole. And then on the x-axis, this is a measure of energy in the common units of watts per meter squared. So up, more energy is striking a particular latitude than down. And there's two lines here. So we have a blue line, and that's the amount of the solar rays that are absorbed by the Earth. And the red line is the amount of that energy that is re-radiated back to space from the Earth. So what do you see here? What you see here is in the lower latitudes in the equatorial region, there's a surplus. So more energy is being absorbed by the Earth than being emitted, and the opposite happens in the polar region. So what that basically means is that if we didn't have the winds and the atmospheric circulation set up, the lower latitudes would just get warmer and warmer and warmer, and the colder latitudes would get colder and colder and colder. So you can see how important that atmospheric circulation is as it moves that surplus heat to where there's a deficit, and it tries to smooth out that distribution across our globe. Okay, so we have this unequal heating on the Earth, but how does that create movement of heat? That's our next question. So warm and cold, the different temperatures create different pressures on the surface. And so warm air tends to rise, and it creates a low pressure system. And so you can think of this as a hot air balloon. Warmer air will rise, and at the surface, there'll be a low pressure. And just the opposite happens with cold air. It's denser, and it falls toward the surface. And if you've ever opened a freezer and seen that dense, cool air fall out, it can toward the ground. That's what's going on there, and it creates a high pressure. And so when you have a high pressure and low pressure, there's airflow from areas of high pressure to areas of low pressure. It's like squeezing a toothpaste. Where you're squeezing it, it's high pressure, and where the toothpaste flows out, it's where there's areas of low pressure. So generally speaking, over the globe, there's a couple circulation cells that set up these what's called these Hadley cells. And so what happens is you get warm air because of the sun is more directly hitting the equatorial region, so you get more warm, buoyant air, hot air rising in the tropics. And as that ascends, it'll either move north if you're in the northern hemisphere, or it'll move south if you're in the southern hemisphere. And it will eventually descend. And it descends at around the 30 degrees north latitude and 30 degrees south latitude. And so where it's rising in the tropics, you get this low pressure system. And then where it descends along these subtropical highs, you get high pressure system. Okay, and this completes one cell, and it happens further north of that as well in a second cell. Now the Earth is rotating as well. So as that air descends toward the ground around 30 degrees north and 30 degrees south, because of the rotation of the Earth, that air will move from the northern areas back down from an area of high pressure back down to an area of low pressure near the equator. And because the Earth is rotating, that air gets deflected. Okay, and so it'll move from the east toward the west. And this is called the Coriolis Effect. And it's one of the more complicated and challenging concepts, I think, in meteorology and climatology to get your head around for people that haven't thought about it for a long time. And I would encourage people to spend a little time YouTubing and learn a little bit about the Coriolis Effect. But nonetheless, so as the air is moving toward the tropics from the area of high pressure toward the area of low pressure, it deflects and it moves from the east toward the west. And in meteorology, we designate the direction of the winds by where they're coming from. So this would be easterly winds. And then of course, to the north of that 30 degrees north latitude, again, the Coriolis Effect has the opposite. As the air moves northward, it deflects toward the right. So again, that's sort of counterintuitive, but I can assure you there's good physics behind it. And just north of the high, then there's westerly winds. Okay, So those cells set up these semi-permanent regions of high pressure and low pressure. And so this line here, this red line is basically where you get the low pressure ascending air from the tropics. And it's not a straight line across the globe because you can see it bends a little bit by South America because the land is warming up at a greater rate than the ocean. But generally speaking, it's around the equatorial region. You get this band of ascending air and low pressure. And then around 30 degrees north and 30 degrees south, you get this band of high pressure. And this high pressure system that I circled here just to the northeast of Puerto Rico is really important for Puerto Rican climate. And so just so you can sort of map this onto that figure that I just showed. And again, the buoyant air around the warmer air around the equatorial region is rising and demarked by this red line here, and then it's descending, and you can see these surface high pressure systems that set up. Okay, so what this means is that generally Puerto Rico is in surface easterly flow throughout the year, and I've highlighted, I've circled Puerto Rico here on the map, and these arrows show you the surface winds. So generally speaking, now you can have weather, and so the direction of the winds can change, but generally speaking, Puerto Rico's in easterly flow. Now, just to the north of Puerto Rico, as I talked about before, there's the westerly flow. And so as air descends from in the Hadley cell, and it moves north from that 30-degree north subtropical high area, it'll get bent toward the right, and it'll be a westerly flow. Okay, so Puerto Rico is just in the easterly flow, but right to the north of it, and where I am, we're predominantly in westerly flow. And that this can actually help explain the paths of hurricanes that you guys pay particular attention to at this time of year and moving into the summer. And so the hurricanes tend to form in the mid or eastern Atlantic, closer to Africa, and they form in these oftentimes under easterly flow, and they move sort of northwestward. And then as they bend around that high pressure system that's set up here, they get entrained in the westerly flow, and you get this characteristic curving pattern where they start in the east, move toward the Caribbean westward, and then they bend and move north and northeastward. So those trajectories are an exact result of the large scale circulation that's set up, and that is principally driven by the differential heating that is going on at the surface. Okay, so that general atmospheric circulation, and I should say that the airflow is also causing the oceans to move, and it's also part of the reasons why we have ocean currents set up where they do. But I'm not going to spend time talking about oceanic circulation, although it plays a really important part in redistributing the heat around the Earth. Okay, but the general atmospheric circulation that I just talked about is sort of the background state. And then superimposed on that are changes from season to season, year to year, and of course longer term. And I like to think of this as sort of like there's like a big symphony going on where you have members of that orchestra that are laying the rhythm, and that's the sort of background state. And then at different times, different instruments come on and play a more influential role than other times. But it's a really complicated system, and that is in fact why no 2 years really look alike, and that there are some general similarities, but they're also very different. And that's because there's a lot of things, there's a lot of instruments in the climate system. So let's just talk a little bit about what causes seasons, year to year, and longer term changes in climate. And let's just think about this from sort of a fundamentals perspective, where we're recognizing that there's a little bit more detail that needs to be put on this, but basically for seasons, what is driving that has to do with the Earth's position relative to the sun, so the Earth's orbit. From year to year, the changes, a large fraction of the changes globally can be explained by what's going on in the tropical Pacific Ocean, and I'm sure many of you have heard of the El Nino Southern Oscillation, so we'll talk a little bit about that. And then longer term, on the order of decades to hundreds of years, not geologic time, not like thousands and millions of years, but longer term. By longer term, I mean decades to 100 years. What's controlling that is basically the amount of energy that the system has to work with. So very briefly, this is something that you all experience, and this is the monthly average rainfall and temperature in Puerto Rico. So the green bars are rainfall, and the blue line is the minimum temperature, and the average is the brown line, and the red line is the maximum temperature, the average maximum temperature. And so you can see a couple clear patterns with temperature. I mean, obviously it gets warmer in the summer. And with rainfall, it's on average, it's pretty consistent from about April until December, maybe January, and then you have a slight break in February and March. So when we think about temperature, it's pretty easy to explain this, and that is just basically when the northern hemisphere axis is tilted toward the sun and we're in our summer, we're under more direct the energy from the sun strikes the earth more directly in the northern hemisphere, and so it's warmer. And the converse happens in the southern hemisphere, and that can explain a large degree the seasonal changes in temperature. When it comes to precipitation, it's that subtropical high that has an important role. And so in the summer, it sits up generally where it is right now, so that the center of that high pressure is to Puerto Rico's north and east. And consequently, you can see not very well, but there's these little arrows and they show you the direction of winds. And so the winds are sort of going like this, clockwise around that high. And so Puerto Rico, you can see, is under the easterly flow, as I mentioned before. But in the winter, that high pressure shifts so that it's more overhead of Puerto Rico, and that high pressure then suppresses airflow into the region and makes for a more stable environment, and so you get less rainfall. Now, that high pressure can wobble, and so there are cases where you have rain in February and March, as evident by these bars here, but just generally speaking, there's more times when you have stable weather in those months than you do in summertime. Okay, so another main reason why you have different temperatures in Puerto Rico has to do with its proximity to the ocean and its elevation. So as you go up in elevation, you're obviously going to have cooler temperatures. And so you see here a map of the average annual temperature, and you can and this is basically showing the elevation as well. And as you go toward the sea, the coastal regions, you get lower elevation and warmer temperatures. It just so happens that in the winter time, you also get warmer temperatures around the coastal regions because the ocean is a little bit warmer, and so that ocean is giving off some heat to the coastal areas. So it helps make it so that the cold temperatures aren't as cold as it otherwise would have been. And also, rainfall is highly influenced within Puerto Rico by elevation. And here there's a direct relationship with temperature. So again, as you go up in elevation, you get, by and large, wetter areas. So the purples and the blues are wetter than the oranges, yellows, and reds. And the reason that is, it's because warm air can hold more moisture. It's a physical property of the atmosphere, such that as air moves over the topography and as it's forced up, it goes into cooler and cooler temperatures, and that air just can hold less water, and so it rains out consequently. So that air is acting as a way to squeeze the atmospheric sponge, so to speak. And that also matters when we think about changing temperatures or just summer months that are hotter than other summer months. If they are hotter, there's more ability for that atmosphere to hold more moisture. So colder air, I have it written here as colder air can hold less moisture than warmer air. And that helps explain why there's more rain in the areas in Puerto Rico where there's higher elevations. And then I just wanted to bring up that in terms of experiencing very hot temperatures, Puerto Rico experiences something on the average of 3 days with temperatures above 95 degrees Fahrenheit per year, which doesn't sound like a lot, but as we'll hear later in the week, even a couple days or even just a day can cause quite a bit of public health impacts. And today I actually went into my office because my internet isn't so good, and I'm in office for the first time in basically 6 weeks, and they've turned off the air conditioning, and it is incredibly hot in here. I'm sweating profusely. But it just goes to show you, it's not even 95 degrees out yet, and inside it can be amplified even more so. And so having the ability to cool yourself during summer months is pretty critical, even if there's just a few days. And then in terms of nighttime temperatures, if anybody has slept in temperatures that are greater than 80 degrees, it's pretty uncomfortable. And people in Puerto Rico experience on average something on the order of 10 extremely warm summer nights. So it doesn't happen as many times as it happens here where I live, but it certainly happens. It's something that we should pay attention to, and it's something that we should think about in terms of how that will change in the future. All right, so in summary, the position of the Earth in relation to the sun drives seasonal temperatures. Temperatures play an important role in determining when and where it rains. But what about year-to-year variations? So that was sort of thinking about it on the average conditions over a year and within a year, the seasons. But what about year-to-year? Many people, I'm sure, are aware of El Nino Southern Oscillation. So we often talk about this in terms of their opposite phases, like an El Nino or a La Nina. And these are climate events that happen every 3 to 7 years. It's not consistent, but there seems to be that pattern where an El Nino will occur every 3 to 7 years, and a La Nina will occur every three to 7 years, and through history. And these are characterized by different sea surface temperature patterns of temperature. So, and I'm showing that in these two figures. So you're seeing on the left-hand side an El Nino event where there is much warmer than average conditions in the tropical Pacific Ocean from basically its center position all the way over to the coast of South America. And the opposite pattern holds for a La Nina condition. It's characterized by cooler conditions. And these matter because the surface temperatures of the ocean then end up interacting with the atmosphere, and it changes the atmospheric circulation, which can have implications for climate all across the globe. So how does this work? Just a little bit about the mechanisms. So you can think of the El Nino has a sort of base condition as well, and it's characterized by sea surface temperatures that are a little bit warmer, and they're surrounded by cooler position temperatures, and it would look something like this. And when you have warmer locations of warmer temperatures, you're going to have warmer sea surface temperatures, you're going to have warmer air temperatures, you're going to have hot air rising. As that hot air rising, it's going to rain out, and so you get a lot of precipitation around the areas where the sea surface temperatures are warmer. And this sets up these two circulation patterns, what are called in the climate world as the Walker circulation, named after the guy that discovered this. And so again, you have this rising air, and as it goes, it cools, and then it moves eastward and then descends around South America, and then moves back toward the center Pacific Ocean. And that happens on the other side as well. And that's sort of the base state. During an El Nino, that sea surface temperature pattern changes, and consequently, you have a shifting position of that hot air rising. And so it moves more toward the east. And that changes the Walker circulation, and it changes the westerlies and the easterlies as well. And I won't get into all of the details, but what goes on in the tropical Pacific Ocean has sort of a rippling effect out across the atmospheric circulation. It's like dropping a stone in a pond, and you see those ripples moving outward. And that same thing happens with El Nino conditions and La Nina conditions as well. So what tends to happen in Puerto Rico is there's a tendency for there to be drier than normal conditions, and there's higher chances for fewer tropical storms during an El Nino. And La Nina is just the opposite, tendency for wetter than normal conditions and higher chances for more tropical storms. Now, there's a lot of year-to-year variability, so these don't always play out like this, but they help us understand just what the chances may be. So again, El Nino is a little bit higher chances for drier conditions, and La Nina higher chances for wetter conditions. And we can see this in the tracks of the major hurricanes. So these are category 4 and 5 hurricanes from 1900 to 2009. And you can see during La Nina conditions that there's just more. So these are plotted, these lines here are just the tracks of the major hurricanes. And the only thing to glean here is that there's much more of them in a La Nina summer than and early fall than there is in an El Nino. And I've marked Puerto Rico in red here, so you can see where Puerto Rico is. So these do matter, and it matters physically. If this isn't just statistics, there's reasons why La Nina conditions can increase the risk of hurricanes. Okay, so moving now to longer term changes. And I started this presentation thinking about the Earth obtains, nearly all of its energy from the sun, 99.9% thereabouts. And over thousands to 100,000s of years, this amount changes by not that much, only about 0.5%. Turns out that over geologic time, that 0.5% is pretty consequential. And it leads to large scale glaciations about every 100,000 years. And that's happened for the last 3 to 4 million years. And so just a small change in that amount of energy globally does lead to these vast glaciations at northern hemispheres and southern hemispheres as well. But when we're talking about it over timescales that are of interest to ourselves over decades to hundreds of years, largely what's driving changes in our climate is going to be the amount of energy in our system. And I want to come back to this idea of electromagnetic heat that comes from the sun. It's of a particular form, and that's really energetic, high amplitude wave energy that is able to pass through because of the chemical properties of the atmospheric molecules. It passes through, those molecules act as windows, and it passes through them and it strikes the Earth. Not all of them, but a lot of them it passes through and it strikes. And as the Earth warms, that Earth re-radiates that heat, but it's of a much longer wavelength. And that wavelength is, it's not a window. Some of the molecules actually capture that energy and they themselves warm up. And that's principally the greenhouse gas effect. Okay, so you've got the energy from the sun that's passing through a lot of greenhouse gases just because it's high energy, it's of a particular form. It warms the Earth re-radiates it. It radiates it at a different wavelength that is not transparent, that the atmospheric molecules are not transparent to those wavelengths. And so they absorb those wavelengths and they heat up. And that adds heat to the energy. that adds heat to the climate system, and then the climate system responds, and it responds by redistributing that heat all around. And so while we may not be able to know exactly how the climate system reacts, fundamentally we know that the climate system is set up to move energy around the system, and when you have more energy in the system, the climate system is going to respond. And so there's a lot of effort going into thinking about, well, how will it respond, in what ways, and what will be some of the impacts. And principally what is driving this long-term change on the order of decades to centuries is the concentration of greenhouse gases in our atmosphere. And you can see here, this is a plot of our temperature over the last 150 years or so. This is in Puerto Rico, so you've experienced on the order of 1.5 degrees Celsius, so close to 3 degrees Fahrenheit temperature change. You know, there's ups and downs for sure. The red line is a 10-year average, so it helps you see the trends, but you can also see that there's significant year-to-year variation. And part of that year-to-year variation is a function of what we were talking about before with El Nino and La Nina and a bunch of other things as well. And so mapped on here at the lower right-hand corner of this figure is just the atmospheric concentrations of carbon dioxide, one of the main greenhouse gases. And so as those are going up, it's leading to some warming of the atmosphere and of the ocean as well. And the climate system is responding, and there's a lot, like I said a minute ago, there's a lot of good research being done trying to figure out how those changes will actually manifest and what the impacts may be. Okay, so I want to close by just summarizing a few points that the climate system is about moving heat around the globe, and it's what the climate system's purpose is, and that there's a north-south airflow in these Hadley cells that create semi-permanent high-pressure areas northeast of Puerto Rico, and that helps influence sort of a persistent easterly surface winds. And it also, in that position of that permanent high-pressure system, is also what creates a few drier months in the winter. And that heat also influences temperature and rainfall patterns through a variety of ways. First, warmer air holds more moisture. Second, that warm surface temperatures in the tropical Pacific Ocean, that pattern determines, can influence global climate through affecting the winds across the globe. And then heat trapped within the system, driven by longer term changes in the atmospheric chemistry, leads to changes on the order of decades to centuries. So I think I'm going to end with that. We can take some questions. I did want to say though that I'm curious. I'm curious about your thoughts on heat and in general, your views on summer heat in Puerto Rico. And if you have the time, I'd be grateful, and some of the members of my team would be grateful, and just completing a very short 5 to 7 minute survey. It's in both English and Spanish. It's anonymous. We don't ask for your name or anything like that. They're just very general questions. And you can get this link, and maybe I can put this link in the chat window. Let's see if I can do that. I'm gonna paste this in the chat window, and maybe Ada or Michelle can post that on Facebook Live.
Yeah, Arnaldo, he already posted it on Facebook.
Great, and so thank you very much for filling that out and for listening to this presentation. And I think with that, I'll just take some questions.
Yeah, we have some questions from the Q&A, and there's a question also on Facebook Live. But the first one, I'll give you the questions from Zoom first, Zach. Okay, so Kimberly Vilar from Arecibo, she asks, what can we do to help our surroundings in order to reduce the heat and alleviate during the climate change season?
Very good question. Well, I think from a personal standpoint, I think when we're talking about the sort of seasonal heat, I mean, it's best to think about your risks to heat exposure, and obviously staying out of the really warm parts of the day, and making sure that you're cooling yourself. And then I also think that, you know, from a sort of an urban planning perspective, there's ways at creating, you know, nice shaded areas, you know, areas that have a lot of asphalt and a lot of materials. Those materials absorb the sun's energy a lot more, so they warm up. And so it's oftentimes within Puerto Rico, within cities, there are areas that are much hotter than let's say parks. And so from an urban planning perspective, just making sure that we're designing our cities in ways that are attentive to making sure that there's enough cool or cooler areas is important. So for the urban planners out there and the architects out there, that's really important. And, you know, then from a long-term perspective, I mean, I think it's a couple things. There's a lot that we can do in terms of, so the climate change topic is usually broken up into mitigation and adaptation. And mitigation is, well, how can we eliminate what's causing or reduce what's causing the climate change? And adaptation is thinking about, well, how can we live better with that change? And I think on the adaptation side of things, again, it's being more attentive to when there is heat, and being more aware of heat issues, and thinking about who's more vulnerable than others, and making sure that our societies are enabling people to have, let's say, the ability to have air conditioning, or that there are cooling centers that people have access to, and that there are public places that people want to go to, like malls. And then on the mitigation side, I think a lot of this has to do with making sure that, you know, our leaders globally understand that this is an issue, that climate change is an issue. From my perspective, it's an issue. But I think also framing the conversation more in terms of opportunities than harm is just a way that I like to frame it. And I think that there's a lot of opportunities in thinking about climate change and mitigating future climate change, while doing that in ways that create really better places for us to live, and places where we're more prosperous. So I think it's a false choice to think about climate change as either we deal with that problem and reduce the welfare of the global community, or we increase the welfare of the global community and not be attentive to climate change issues. I think that's a false choice. We can do both. That was a long, rambly answer.
It's okay. Zack, is there a possibility that you can take out the share feature, so our friends on Facebook Live can see us both?
So stop sharing?
Yes, yeah.
Yes.
Thank you. So we have another question. I told you one from Zoom, and now I'm gonna tell you one from Facebook Live. From Facebook Live, we have Luis Cintron. He asks, why sometimes, not always, hurricanes come from the west and not from the east? I think you explained a little bit about that, but.
Yeah, and so sometimes, yes, so it depends on where you are in the Caribbean. If you're a little bit toward our north, generally the trajectory or the paths of the hurricanes sort of curve toward a more northeasterly direction, and so they're coming from the west. And if you can think back to that figure that I showed of that high pressure system. And so how it works in the Northern Hemisphere is when you have a high pressure system, there's going to be clockwise movement around that high pressure system. So that the position of that high pressure system can move. So if it moves south, you end up having airflow from the west further south than you otherwise would have. So that can partially create a situation where you have a hurricane that develops and moves develops to Puerto Rico's west and moves from the west to the east. It doesn't happen very often though. But it's all about what the current weather patterns are like and the positions of these highs and lows that matter. Generally speaking, the trajectories, as I showed in those figures, move from the east toward the west, and then they recurve as they move north back toward the east.
Okay. Thank you. So now from our Q&A in Zoom, we have Luis Torres. He asks, in the future, is the sun expected to lose the ability to emit heat?
Not that it matters for us. So billions of years, the sun eventually will burn out, but billions of years from now. So yeah, I think we'll probably be long gone by the time that the sun matters.
We have two more questions. Luis Torres also asks, could it be possible that in Puerto Rico at some time, due to the weather change, it could snow?
Boy, I would turn this over. How cold is it?
No.
Highest elevation?
No. No, we're not gonna get any snow. I mean, because of the latitude and no.
Okay.
The lowest temperature that we've had is about 40 degrees in the mountains. Even in the Dominican Republic, up in the very tall, very high mountains, it can get some frost. And we even got some frost, but no snow. No, that's not gonna happen.
Ada, one of our viewers said that in Hawaii it has snowed. Why can't then? But it's because of the latitude, right?
Well, it's also because Hawaii has a big volcano that gets up to, I think there's actually even a glacier on top of Hawaii. So it gets up to really cool climate. So as you go up, generally speaking, every 1,000 meters, you cool by about 10 degrees Celsius, if I'm getting that right.
Yeah, you're right.
So, if you go up just 3,000 meters, about 10,000 feet, which I believe is what the elevation is at, maybe a little bit less than that. It's a temperature change on the order of 30 degrees Celsius. So it can be quite cold. Elevation matters. So you just don't have as high mountains in Puerto Rico as you do in Hawaii.
Okay, we have a question from our, sorry, what?
No, that I was gonna say that the freezing level in our latitude is approximately like 15,000 feet. So you would have to get to 15,000 feet in order to get snow. And we don't have those heights here in the mountains.
There you go.
So we have other question from Facebook Live, and it says, does high pressure that moves southwest in the middle of the Atlantic avoids hurricanes being formed near the coast of the USA?
I'm sorry, could you repeat that? You cut out a little bit.
Yeah. It says, does high pressure that moves southwest in the middle of the Atlantic avoids hurricane being formed near the coasts of the USA?
Does it avoid hurricanes? I'm not sure it would help steer the hurricane. So it's like hurricanes would if anything, that position would influence the trajectory or the path of the hurricanes.
Yeah, it depends on where the high pressure is located, and that because that is the wind that drives the movement of these tropical cyclones. They move over this river of air, and it depends on where is it located. Is it farther from the east, located more closer to Europe, or is it closer to the United States, or is it centered closer to the northeast of the Caribbean? It depends, and it's a delicate balance and dance in a way how the tropical cyclone moves along these high pressure levels. So that's why sometimes it's very difficult to forecast, because you don't know how much it is shifting to the east or shifting to the north or south, and that depends on also the upper levels of the atmosphere, how upper troughs or vaguadas are moving, and then they pick up the circulation of the cyclone, and then it can veer and then not touch Puerto Rico. It depends on many factors, but it certainly depends on how the winds steer the movement of the tropical cyclones.
And we have a last question from Kimberly Villar. How new is the term of El Niño and La Niña been used?
How new did you say?
Yeah, I think she meant, or how old, because she asked how new is the term of El Niño y La Niña being used. So.
Yeah. For how long have they been using? So that's something that they has been using for a very long time. I mean, Indians and people in my family is from Ecuador, and you know, this is, I mean, the history there is for thousands of years. They know of this phenomena. However, now that we have instruments and we can monitor it and we can see it, it's how we can we're able to make teleconnections with other parts of the world. But the event, the El Nino event, just as the Saharan dust storms, they have been there for millions of years.
Yeah, and I would just add that it's a phenomenon that was initially found by Peruvian fishermen, because they noticed that the fish stocks would ebb and flow as the temperatures and the sea surface temperatures changed. Really, in the 50s, we started being able to monitor get actual measurements, and so we were able to start developing maps, and that really we were able to do that more forcefully in the 80s. As we put buoys out there and had ships collecting data, and of course that our ability to monitor the sea surface temperatures, that's only increased as now we can use satellites. And really the scientific community was first able to predict to some degree of accuracy, not completely accurate, but was able to predict what the state of the tropical Pacific Ocean would be in only back to about, it first began in the late 1990s, mid 1990s or so. So it's not a long history in terms of predicting and trying to scientifically understand what the impacts, what's causing it and what are the impacts. And I would say that there's still a lot of scientific questions that are unanswered about ENSO, El Nino and La Nina, and we're learning more every single year.
So I will do the last question, Zack. So what do you think then the route should be toward building resilience, especially as we face a very active hurricane season in 2020? What are your recommendations?
Yeah, I think, well, I think personally, we have to become aware of what the risks are. And I think a lot of people have a lot of experience in Puerto Rico of hurricanes, but just a little bit of advanced warning and preparing really quite in advance is really helpful. And so not waiting for the last minute, so to speak. And just in terms of thinking about resilience, thinking about what the impacts could be and whether or not, whatever those impacts are you able to function under those conditions, and going through those kinds of thought experiments and really developing, your own resources and your own capacity to be able to, whatever the weather throws at you, being able to weather it. So I had an old professor once say, it's a saying that I think is really important, which is, we'll weather the weather, whatever the weather, whether we like it or whether we don't. So recognizing that the weather is going to throw a bunch of curveballs at us, making sure that we're able to deal with whatever that weather is important. And but I also think that there's a role for us to play to making sure that the institutions that are set up to help us are also held accountable and are also preparing. I mean, we can't do it all on our own, and we need to make sure that our leaders are taking these threats seriously and have plans, and that's going to take people that have interest in this, volunteering sometimes their time, or just making sure that people are listening, because there's only so much individuals can do, and we really do need to create systems that have the resources to make it so that everybody has access to information and the resources to recover and to prepare. So it's not a great answer, but I think it's both at an individual personal level, doing what we can do, but also recognizing that we can't go the full distance on our own, and that we do need functioning systems set up, and people that are running those institutions, if you will, have to be held to account for that.
And also it should start at the community level, right? The role that communities have in all of these are so important. We cannot ask the government, and we know as a fact that government cannot handle all the situations. It's too much. It's energy, communications, equipment, volunteers. I mean, so much goes on when we have catastrophic events, that we have to start at the community level, understanding the needs, and then working with those needs right now. And although we are all in a lockdown, we still can do some work, and at least lay the foundation for building more capacity, more resilience, more preparedness, so that when we are faced with the emergency, either is an earthquake, either is a hurricane, or either is a drought, then we have those things that we need. We need priorities.
I want to add to that, because I think that's a really good point. When you look at the research on resilience, one of the things that always comes through as being the asset or the capacity that is so vital, it's connection, and it's people. It's what we call in the academic world like social capital. It's how many people that you are in contact with, and how big your networks are, and it really is. It's about the community, and communities can take care of themselves. And it is so important, I think, to work on across all of those levels, from the individual to the community to the sort of national level. And resilience is it's a complicated subject, and it requires a lot of activity and effort.
Thank you, Zack. I mean, this has been enlightening, and we are so thankful that you have been able to be part of Ciencia Virtual with EcoExploratorio. I mean, you are international scientists here in Puerto Rico, from Tucson, Arizona to Puerto Rico. Oh my goodness, these platforms are amazing. I mean, they can connect and build communities, right? No geographical borders, just communication and will to educate and make changes.
Well, thank you so much. I really appreciate it. It was fun, and I hope the participants are able to tune into some of your other talks. It's a really great resource. And I hope
Thank
everybody
you.
stays safe and well.
Thank you, and you too. Okay, so this was Dr. Zack Guido, Assistant Research Faculty del Arizona Institute of Resilience de la Universidad de Arizona, para el EcoExploratorio a través del equipo del recinto de ciencias médicas que están haciendo un trabajo extraordinario sobre salud pública y calor en el área de Puerto Rico. Así que agradecida del doctor Méndez, que yo sé que nos está escuchando actualmente, y a cada uno de ustedes por ser parte de la comunidad del EcoExploratorio. Te lo entrego, Michelle.
Gracias, Ada. Y pues muchas gracias a todos por participar de este webinar traído a ustedes por el EcoExploratorio Museo de Ciencias de Puerto Rico. Gracias a nuestros auspiciadores por ayudarnos a hacer esto posible, como siempre. Y gracias nuevamente a nuestro recurso de hoy, Dr. Zack Guido. Y recuerda que puedes encontrar esto y todos nuestros webinars en nuestra página de YouTube. Para más información, accede a nuestra página web www.ecoexploratorio.org/ciencia virtual. Y recuerda que si deseas volver a ver este o alguno de los pasados webinars, puedes visitar la galería de videos en el Facebook del EcoExploratorio o seguirnos en YouTube para que recibas una notificación cada vez que publiquemos uno nuevo. No olvides seguirnos también a través de Facebook, Twitter e Instagram, donde encontrarás el calendario de futuros webinars y cómo puedes también registrarte. Recuerda darnos un like y compartir nuestras publicaciones para que más personas disfruten de nuestras actividades. Para más información de nuestros servicios pueden comunicarse al 787-281-9090. Escríbenos a webinar@ecoexploratorio.org, cualquier cosa. No te pierdas de nuestro próximo webinar, que sería mañana, martes. Ahí se me fue el día. Es el 12 de mayo, en el cual vamos a seguir con el tema edición del calor y empezaremos a las 11 de la mañana con lo que es la flora y la fauna ante la sequía con nuestro ecoexplorador Roberto Sánchez. A la 1 de la tarde seguiremos hablando sobre el calor en las zonas urbanas y cómo disminuirlo con nuestra ecoexploradora Esmeralda Torres. Y a las 3 de la tarde tendremos con nosotros nuestro recurso Ernesto Díaz, director de la Oficina de Manejo de Zonas Costaneras y Cambio Climático del Departamento de Recursos Naturales y Ambientales, hablando sobre la ruta hacia la resiliencia ante el cambio climático. Recuerda, quédate en tu casa junto a la ciencia divertida del EcoExploratorio Museo de Ciencias de Puerto Rico. Y gracias por el apoyo. Que tengan todos un bonito día.